What is the difference between a nova and a supernova? Why does the moon look upside down when you're in the southern hemisphere? And is there any limit to the periodic table of elements? All this and more in this week's question show. Welcome to the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I will gather them up and I'll answer them here. Before I get into this week's show, I just want to celebrate that this is the 25th anniversary of Universe Today. In other words, I have been a space journalist for 25 years. I founded the site on March 23rd, 1999, and here I am, 2024, still doing some version of the same job. So thank you everybody who has supported Universe Today over the years, both our patrons as well as everyone who has gone to the website, everyone who subscribes to the newsletter, watches this stuff on YouTube and so on, listens to the podcast. I really appreciate everybody's support and this incredible team of writers and video editors and programmers, audio editors that work with me to bring you all of this material. We love it. We've been doing it for 25 years. I've been doing it for 25 years. And we will only stop when the robots do a better job than we do. And I think that'll take a while. So here's 25 more, at least. All right, let's get into this week's question show. Robert W. Cote. How do we account for gravitational lensing of the cosmic microwave background radiation? Do we really have an accurate model of where all the matter, both light and dark flavors in the entire observable universe is enough that we can reliably unlens the CMB? When astronomers first discovered the cosmic microwave background radiation, and over the years as different spacecraft like COBE and WMAP were launched, they were able to map the cosmic microwave background better and better over time. And one of the things that they knew was that there was a little bit of fuzziness in the cosmic microwave background. And this was coming from the combined gravitational lensing of all of the photons that were traveling from 300,000 years after the Big Bang to us today. And that these photons had to go through all of these galaxy clusters and past galaxies. And it's kind of amazing when you think, like, each one of these photons survived the entire journey. They traveled for 13.8 billion years and they never hit anything. They never hit a star, they never hit a planet. They just went from leaving a point in space, traveling for 13.8 billion years, and then arriving at our detectors. But one of the hopes when the Planck satellite was developed by the European Space Agency, that when it would launch, one of the things that it would do is that it would be so accurate that it would be able to measure the amount of gravitational lensing, the combined gravitational lensing that went on with these photons. And then the hope was that then they could de-lens the CMB, that they could sharpen it by knowing essentially on average how much photons were shifted away from their positions. You could then go back and look at the original CMB measurements, and then you could change them to adapt for the gravitational lensing. And so they were able to do that. And with enormous accuracy, they were able to get like 9 sigma accuracy in the measurements. And so in addition to measuring the cosmic microwave background with more sensitivity than had ever been done, it was able to do this de-lensing of the CMB. It was also able to measure the lensing of the polarization of the CMB. And so, you know, when you wear polarized lenses and you're sitting in a 3D movie and then you like take two of the lenses and you put them beside each other and they block the light out, or you turn the light and you can see different parts of the movie, right? That's the polarization of the light that's coming from that movie. It's done on purpose to give one eye one vision and the other eye a different view of the same movie. And so they were able to actually measure the effect of the gravitational lensing on the polarization in the CMB. So it's like safe to say that the Planck mission was one of the most successful science missions, and this de-lensing was just one of its to-dos that they were able to check off when they wrapped up the mission in 2018. I hope you noticed the Star Trek planet name that appeared above my shoulder. This is a way for you to vote, to tell us what you thought was the best question of the week. And last week's vote was for dark star 420, isn't there a star heading towards us from the Large Magellanic Cloud? And it sort of led into this really fun conversation about stars mixing between the Milky Way and Andromeda, and led to some news that was reporting. So thanks for everybody who voted. Now we're going to put up a different Star Trek planet name above my shoulder. I'm probably pointing at the wrong shoulder. Maybe it's the right one. And then you wait until the very end of the episode and then just write down in the comments the planet name that you thought was the best question. Then we'll gather it up and we will celebrate the vote next week. Whitney Adams 4008. Can you please explain the difference between a nova and a supernova? I've heard there is potentially an upcoming nova event and I want to know more. No problem. Yeah, so I want to talk about the event first, and then I will sort of wrap that up in the difference between a nova and a supernova. So the event is that there is a star called T Coronae Borealis that has been known to flare as a nova every 80 years or so. And astronomers have measured its brightening several times in history, and the last time was in 1946. And Corona Borealis is a tiny little constellation that is smack dab in between Hercules and Bootes. So it's very familiar in the Northern Hemisphere. If you know where Hercules is, it's to the right beside Hercules, in between Bootes. Bootes looks like a kite. Hercules looks like a dude. And it's right in between those two. And one of the stars in that constellation is going to brighten. But I need you to prepare yourself for what this is that you're about to see. This star is practically invisible to the unaided eye. It's magnitude 10. You need a pair of binoculars or a small telescope to be able to see it. And over the course of this nova event, it's going to brighten to magnitude 2 at the most. And just to give you a comparison, the North Star Polaris is magnitude 2. Not the brightest star in the sky, but it's fine. You could see it. And so unless you know exactly where you're looking, you won't even know that there is a new star in the sky. It'll be around for a couple of months and then it will fade away. So I think a lot of people are quite excited. So imagine, right? You go outside and there are thousands of stars that you can see with your eyes. And there's a new one that's roughly the same brightness as many other stars. And then it's gone again. So, it's scientifically, it's incredibly fascinating, and it's going to be really cool if you know what you're looking for. And so go out now, learn where Hercules is, learn where Bootes is, and then learn where Corona Borealis is, smack dab in the middle. Learn those constellations. Both are really fascinating. There's a lot of really interesting things in both of those constellations, and that part of the sky to the Northern Hemisphere is quite easy to find. A lot of really interesting things there. So that's the preparation that I recommend. So what is it? What is a nova and what is a recurring nova? So a nova occurs when a white dwarf star has siphoned off material from a companion star. So you can imagine there's a white dwarf star in orbit around another star, and they're close enough that there is this tidal tail of material that's going off of the star and down onto the white dwarf, and it's wrapping around the outside of the white dwarf, building up into this layer of material on the outside of the white dwarf. And at a certain point, so much material is on the outside of the white dwarf, it's heated by the gravitational pull that is squishing it down, that it undergoes this thermonuclear explosion, explodes off the surface of the star. The star is very bright for a short period of time, and then it fades again, and the process starts again as more material starts to accrete onto the outside of the star. That is a nova, and nova happen on a regular basis. Astronomers know of many of these recurring nova, and then other times they find these nova for the first time. So that's a nova. Nova is a white dwarf star that experiences a temporary outburst because it has stolen material from a partner. A supernova is when a star explodes. And there are a variety of causes that can get you to a supernova. So one line of them is that you have a star that's much more massive than our sun. It's fusing material in its core. It is no longer able to fuse in its core, and the outward pressure of the light stops, and all of the outer layers collapse in on itself, and it explodes. And that's called a core collapse supernova. And that's like the simplified version. But there's another kind of supernova known as a type 1a supernova. And these are explosions of white dwarf stars that have reached 1.4 times the mass of the sun. So when a white dwarf, like the one that our sun will eventually turn into after it finishes the main sequence phase, it will become this object that is less than 1.4 times the mass of the sun. Like obviously, right? Like the mass is 1 times the mass of the sun. And so it will be less. It is essentially the exposed core of the sun. But if, again, the sun was next to some partner star and it was siphoning material, building it up on its outer surface, it would be creating these layers. They would blast as nova, but some would be left over and they would pull in more material and blast as a nova. And as slowly over time, it would accrete enough material that it would reach this thing called the Chandrasekhar limit, which is 1.4 times the mass of the sun. And when that happens, then you don't just get this flash off the surface of the star, you get an explosion. The star disintegrates entirely and creates this incredibly bright flash. And astronomers use these type 1a supernovae as a way to measure distance in the universe, because that number, that 1.4 times the mass of the sun, you know intrinsically how bright the explosion is that you get to see in the sky. And then when you measure the brightness that you can see, then that tells you the distance. And if that happens to go off inside a galaxy, then you know how far away that galaxy is. And because they're so bright, these are very useful way out to billions and billions of light years away for being able to measure distance in the universe. Dreamcast Night. Could the Hubble constant be corrupted by the galaxy's movement towards the Great Attractor? And has anyone been looking for such evidence? That's such a great question. And that's a very clever insight that you had. So the question is, like, we know that there is this discrepancy in the measurement of the speed of the expansion of the universe, that for the methods like using Cepheid variables or even the type 1a supernova, you get one measurement. And then when you measure the expansion rate of the universe based on the cosmic microwave background, you get a different measurement. And that was thanks to the Planck satellite that I mentioned in the first question. Wow, the whole thing is coming together. Anyway, and this is called the Hubble tension, the crisis in cosmology. And so the question that you're asking is, like, we know that the Milky Way is part of this large supercluster of galaxies, and we can see that galaxies are sliding towards some center of gravity that is on the far side of the Milky Way. And the question you're asking is, well, like, could that motion of the Milky Way as it's getting pulled towards the Great Attractor, like all these other galaxies, could that account for some of the error in the Hubble tension? And the answer is yes. In fact, astronomers have looked for this. So we know that the Milky Way is part of the local group. The local group is part of the Virgo supercluster. The Virgo supercluster is part of the Laniakea supercluster. It's sort of like the largest structure. It's 500 plus million light years across. It contains about 100,000 galaxies, and it is influencing the Milky Way's movements through the universe. And so astronomers recently did a study where they calculated how much effect would this motion of the Milky Way's movement through the Laniakea supercluster impact our measurements of the Hubble tension. And the answer they got was not zero, about 2 to 3% of a modification on those measurements. But here's the problem. It's in the wrong direction. So in other words, that if you account for the Milky Way's movement towards the Great Attractor, you would actually get an even greater difference between the measurement in the Cepheid variables and the measurement in the cosmic microwave background. So yes, the effect is there. And no, it doesn't solve the problem. If anything, it makes it worse. Paul Lathrop. I live at 43 North Latitude, and all my life I've seen shadows on the moon go from side to side. And this past week, when I was visiting at 18 North Latitude, the shadows seem to be going bottom to top. What gives? Now, I don't know exactly sort of where you are and what you were seeing, but I have a similar situation. I live at 49 North Latitude, and I have been to places like Costa Rica, which is closer to the equator. I'm not exactly sure where it was. And I've also been to Australia. And yeah, when we are, like, I'm sort of imagining standing out on my deck and I'm looking at the moon and I'm seeing the direction that the crescent moon makes and which side of it is a shadow. And yet when I was in Costa Rica, closer to the equator, the whole moon felt like it was rotated, and it was more like the bowls of a horn. Bowls of a horn. It was more like the horns of a bull. And yet, when I was in Australia and I looked at the moon, it was completely reversed. And so if it's this way, and I don't know whether it's going to be reversed or whatever, but if it's this way when I'm at home, it's this way when I'm at the equator, and it's this way when I'm in Australia. It's about where I am on planet Earth. So when I'm standing close-ish to the North Pole of the Earth, I'm looking at the moon from one perspective. But when I'm at the equator, I'm effectively on my side and I'm looking at the moon. And then when I'm in Australia, I am upside down looking at the moon. And so that change that you're seeing in the direction that the shadows of the moon are happening is entirely based on your position on planet Earth. And you just experienced like one of the obvious implications of being on a spherical Earth when you look at the moon. Very cool. Pelican 666. Any thoughts of putting the deep space network in space? Maybe only need one location. There are no plans to build the deep space network in space today, but it would be an amazing improvement to the current capability of our spacecraft. So right now, there are a large number of giant radio dishes down here on Earth, and these are the Deep Space Network. And these are what NASA uses to communicate with the different spacecraft that are all around the solar system. And in fact, you can actually go to the Deep Space Network website, and then you can see all of the different radio dishes, and you can see which ones it is communicating with at which time. So you can see that this 70-meter dish in California is talking to Curiosity, and that 70-meter dish in Australia is talking to Perseverance, and so on. And the position of the dishes is that they can provide coverage of the entire solar system as the Earth is rotating. The problem is that it is oversubscribed and that we are just launching more and more spacecraft, and not just what NASA is launching. You've got the European Space Agency, you've got Japan, you've got all these different agencies, and they are all attempting to communicate with their spacecraft. And the bandwidth is running low because a radio dish that is looking at one spacecraft cannot then receive any data from any of the others. And so they all have to queue up and wait for time on these big dishes as they track the different spacecraft, send and receive all the data, move on to the next target, send and receive all the data. And so just like in general, more dishes are needed to keep up with the increase in capacity requirement from all of these additional spacecraft. But the big problem is that the farther away a spacecraft is, the more signal attenuation that you get, the slower the bandwidth that you can receive from that spacecraft. Like with New Horizons out at Pluto and beyond, it's only able to send in a couple of bytes a second when it's attempting to transmit at a much higher bandwidth. It's just that the signal is very weak by the time it reaches Earth. You've got to have a gigantic radio dish to be able to receive the transmission. So there are a couple of solutions to this. One is to switch the way transmissions are done. And recently with the Psyche probe, NASA tested out using laser communication to send messages to Earth from the spacecraft. And they were able to send just an astonishing amount of data. And they built a hybrid version of one of their big dishes where it's got this traditional radio dish, and then it's got a laser like a telescope built into the middle of it. It's able to receive laser signals as well. And they were able to find that they were able to get about 40 times as much bandwidth with this hybrid approach. And so you can imagine, okay, all future spacecraft are going to have these laser transmitters in addition to their radio transmitters. And that's going to allow them to send and receive communications at dramatically higher bandwidths. That should decrease the load across the Deep Space Network. But the other thing you could do is you could put these spacecraft out across the solar system so that they can receive the signal and then transmit with a much larger transmitter. And then that means that you don't have to put as much hardware on the spacecraft themselves, just enough transmitter to reach the relay point and then be able to send that data back home. The Chinese Space Agency just launched one of their relay communications satellites called Chichao 2. And this is the second one. The first one helped with an earlier mission at the moon. And this is going to be at the far side of the moon. Well, it's actually, this spacecraft is in orbit around the moon, but it's able to see both the far side of the moon and Earth at all times from its orbit. And so as the Chang'e 6 mission goes to the moon, does a sample return mission in the next couple of years, from the far side of the moon, this relay satellite is going to be able to receive the signal, send it to Earth, and to be able to receive commands and send them down to the spacecraft. And so you're going to probably see this increased infrastructure over time of relay spacecraft. You could have some big transmitter just sitting at Mars that is then collecting all of the information from all of the rovers, bundling it up into one big package, sending it to Earth with a big transmitter. That would be a huge savings in sort of radio telescope time here on Earth. So more infrastructure is always needed. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. That's like 3 hours long. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Gary Hash, Martin, Bill Doster, Jamie D, Dougie Stewart, Phillies 2012, Stephen Krasaki, Mike Keats, Black Hole, Robert Revak, K220 Mark, Michael Costigan. Join the club at patreon.com/universetoday. Relin Fellner. Should NASA consider assembling an Aldrin cycler between Earth and Mars before sending humans, kind of like the Lunar Gateway? So the Aldrin cycler, this is a spacecraft that is proposed by Buzz Aldrin and has been proposed in other scientific concepts as well. And this is a spacecraft that would travel from Earth to Mars and back and forth, kind of like a regular ferry service. And a good example of something that's like that is, I don't know if you remember in The Martian, there was this spacecraft that was carrying all of the astronauts to and from Mars. And then they switched to their own descent vehicle. And this spacecraft was making a sort of return trajectory from Mars. And so the idea is that you've got this spacecraft that is making this regular just trip, orbital, from Earth to Mars, back and forth. It requires minor changes to its orbits to be able to make the meeting points of both Earth and Mars. And so as it gets close to Earth, then the astronauts launch in their rocket, and then they rendezvous with the cycler, they get on board, and then they fly on it. And it's got like better facilities, lots of food, lots of power, lots of comforts on it as they make the long trip, better radiation shielding as they make the trip to Mars. And then when they get to Mars, they hop off and maybe they go to Phobos, or maybe they actually do an entry onto Mars. And then another crew launches off of Mars, docks, rendezvous with the cycler, and then follows it back to Earth, and then they return to Earth. And there's a lot of really good reasons. Like, this provides redundancy and safety for the astronauts during that multi-month, it could be 6-month, could be 9-month trip from Earth to Mars and back again. And to be able to have a safe place where people can be, where you know it's done, it's launched, all of the materials on it, has everything that the humans need. All they have to do is get on their Dragon capsule, like they launched to the International Space Station, and just meet with the cycler. So that's a great idea. Now, a lot of people think that it's not necessary, that it's kind of redundant. And so, I'm sure if you ask someone like Elon Musk, he'd say, well, just launch on Starship. Everyone gets on Starship, they take all their gear, they fly to Mars, they land, and you don't need this complicated, intense ferry system to take people to and from Mars. And we'll see how it all plays out, but I think the idea is pretty cool. Dop3 Dog, is there a limit on how many elements can fit on the periodic table? I think the question you're really asking is there a limit on how many protons that you can pack together into a single atom? And like, theoretically, no, there's no limit, but practically there absolutely is a limit. And there are certain atoms that are stable. And you don't have to get very far up the periodic table of elements to start reaching unstable atoms. Like even uranium, plutonium, these things are unstable and they fall apart, decay after a certain amount of time. But in giant particle colliders here on Earth, scientists have been able to build atoms, and I don't know what the current number is. It's in the 120s, I think, for the number of protons that are on it. But these things are incredibly unstable. They fall apart within a fraction of a second, and they're not seen naturally in nature. And so a question that people ask is, like, could we expect there to be some island of stability where we might, with bigger and bigger particle accelerators, get to a place where we're able to build atoms that have 200 protons and they're stable and they're unobtainium and you could use them for some cool effect. And the answer is probably not. And that's because the universe is the greatest particle collider we can possibly comprehend. Think about a kilonova where you have two neutron stars. So each one is the result of a supernova. They are the remnants left over. They are the size of a city, and yet they have several times the mass of the sun. They're incredibly dense and compact. And you take two of these things and you smash them into each other. Just like, think of the masses involved. When astronomers saw the kilonova explosion several years ago, the first one, they saw many Earth's worth of gold produced instantaneously in this colossal explosion. And you have got to assume that even more massive particles were formed in this kilonova explosion. And yet they all would have just decayed away almost instantaneously. What's left are the stable elements that we see in the periodic table. Like, the periodic table isn't a rule of nature. It is a handy way for us to perceive the elements as we find them in the universe when we think about how their masses, their behavior, how their electron shells work. And the universe, when it explodes stars and crashes neutron stars together, can come up with vastly more complicated particles than we can comprehend, and yet we don't see them. So if the universe could make them and they were stable, then we would see them, and we don't. So we can just safely assume that we will never make them either. Cosmic collisions. How interested in science and astronomy were you as a teenager? What was your high school experience in physics? I was super into space my whole life. As a child, I had a book of Our Universe, which was like a Time Life series of books that you could receive and pay in installment payments. And they had something else on searching for underwater treasure and a couple of other books. But the Our Universe one was the one that I loved. I had the original version before the updated content for the flybys of Uranus and Neptune by the Voyagers. And then when I was in high school, I got into astronomy again. In fact, there was a garage sale and somebody was selling all of their sky and telescope magazines. They had just piles and piles of them. And so I got them for cheap and I just went through them. Magazine after magazine, reading about space, looking at the pictures and looking at the ads for telescopes. And then when I was 14 or so, I bought my first telescope. I went to Vancouver. There's a telescope manufacturing company in Vancouver, and I bought, it was a 4-inch Newtonian reflector on, or it's like a 4.5 inch, 4-inch on an alt azimuth mount. So it's like up, down, side to side, didn't track the sky at all. And I was out every night with this telescope and I learned my constellations and I observed all the planets and I saw, galaxies and star clusters and things like that. And then I would set it up when my parents had parties, and I even organized star parties on this island that I grew up with in Canada. And then when I was in high school, I studied journalism in my high school newspaper. And I reported on things you could see in the night sky every month. So I talked about how you could find the Big Dipper, or I was really intense. And so my physics and math and all that was fine. I went into engineering at University of British Columbia. So I had, I took calculus in high school. I took physics 12. I took chemistry, algebra 12, all of the prerequisites. And then I went to engineering and really didn't enjoy it. And so switched and went into computer science, and like my career was working for a web development agency out of Vancouver, and also started a software company and various things like that. And so I sort of forgot about space in my early mid 20s. And it wasn't until I was 28, 27 I was reading The Case for Mars by Bob Zubrin and Pale Blue Dot by Carl Sagan, and was just getting into space again. And there weren't a lot of great resources back then. You read books. This was sort of before the World Wide Web was really starting. But then I watched the landing of the Mars Pathfinder mission with the little tiny rover that it deployed. And we could watch this live. I was at work and we were watching all of the updated information that was coming from this mission. Wait, was it Sojourner? Yeah, Sojourner was the little rover. And then I was like, you know what? I want to start a website about space and astronomy just because I want to learn more about this and I want to cover a bunch of this stuff. And that was in 1999. So 25 years ago when I started Universe Today. So I've always been into space and astronomy. I kind of forgot that I loved it so much for my early 20s and then found it again and then turned it into a career. Daniel Roach, what is the best thing to see from a southern latitude? So there are four things that are extremely cool to see from the southern hemisphere. So those of us in the north, we can't see these at all. It's only when you get closer to the equator that you can actually see them. So I would say the first thing is the Magellanic Clouds. These are kind of like mini versions of the Milky Way. They look like puffs of cloud in the sky. And when you go outside, if you know where to look, you can see the Milky Way and it's sort of stretching across the sky. And then you see these two clouds that are close to the Milky Way, but are very distinct. They look good in dark skies. So that's the first thing. The second thing that sort of blew my mind is the largest globular cluster that we can see is visible, Omega Centaurus, the Omega cluster, and it is the biggest. And I got to see it I was at a star party in Australia, and I got a chance to see it for the first time. And it's amazing, just like a colossal globular cluster. And they're probably one of my favorite sky objects. The next thing is that you can actually see Alpha Centauri. You know, we always talk about Alpha Centauri. It's the closest star to the sun. And yet, for most people who live in the northern hemisphere, you can't see it. And so it's sort of weird to think about this hypothetical star that we just never see. And yet you go down to the southern hemisphere and someone asks someone who knows the sky, point out Alpha Centauri. Oh, it's right over there. That's Alpha Centauri. That's that closest star that we've heard so many stories about. And I'd say the last thing, and maybe this is about being closer to the equator, but when I was in Australia, the Milky Way goes directly overhead. From my perspective, the Milky Way is down at the horizon. It just rises above the mountains. I can see some of the constellations in the Milky Way, but then it comes back down. And so to see the heart of the Milky Way, the very core of our galaxy, directly overhead, which is like the best viewing, is just mind-blowing. And in fact, when I was in Australia, also Saturn and Jupiter, a bunch of planets were also in that same area, directly overhead. And that is not an experience that I am accustomed to have to crane back to look straight up to see planets. They are always down close to the horizon because of my position on the globe. So I highly recommend, if you've never seen the sky from the southern hemisphere, you should definitely do it. And of course, that weird moon is upside down. That's so bizarre. Nomad 77CA. Why were stars in the early universe so much larger than the stars today? From what we can tell, stars today are limited by the amount of mass that they can accrete. And it's about 100 times the mass of the sun. Maybe it's a little more, maybe 150, maybe it's a little less. But what happens is, as this giant cloud of gas and dust is collapsing down into the star gets hotter and hotter at the core, and then it starts to blast out winds, stellar winds. And over time, the stellar winds balance out the infalling material. It heats up the entire rest of the nebula in its environment so that it no longer wants to collapse down. And so the star, as it forms, puts on the brakes of its own development. And so we just don't see stars that are more massive than this. They all are they're limiting their growth. But it's believed that the earliest stars in the universe, the ones that were formed just out of the primordial hydrogen and helium left over from the Big Bang, they were capable of getting vastly larger, maybe hundreds of times the mass of the sun, maybe thousands, maybe tens of thousands, maybe millions. Like, we just don't know still. And it's believed that it comes down to the heavier elements that are in the star, the pollution, the metal pollution. And of course, astronomers think that anything heavier than helium is considered a metal. And so when they talk about metal pollution, they could very much be talking about oxygen, but still that metallicity of the star has some effect on halting its growth. But there's probably more to it as well. So, really the question is, you can't get a star without cold gas. You need to have large reserves of cold material. If the material is very hot, then the atoms are jiggling and they don't want to collapse down. You don't want to get a star. And so when you had some cloud of gas, it's able to cool down so that it's, almost no motion in the particles, then the gravity can pull it together. Usually you'll get some kind of event that gives it a kick, that begins this collapse. But it's possible that these largest objects are somehow interacting with their environment in a way that maybe the magnetic fields, as they're setting them up, are able to cool down the gas and maybe channel away the hot gas away from the star and funnel cold gas into where it's forming this material. So this is like a big question. Like, we still don't really know this. And there are, this is at the very limits of what the James Webb Space Telescope can perceive. Maybe if it sees a bunch of gravitationally lensed galaxies, it might be able to see examples of the first stars forming. More likely, it's going to be able to find the pollution that came from the first stars in galaxies. And it looks like this has already happened, that James Webb has been able to find galaxies that have the results of those first stars dying, and maybe you can work back forensically to figure out how those first stars formed. But this is still a big unsolved question in astronomy right now. And the answer to this question might help answer the other big question that astronomers have, which is, how did supermassive black holes get so massive so early in the universe? Like, we think that black holes came together one by, you have a star, dies, black hole, another star, dies, black hole, the two black holes come together, you get a more massive black hole, they find another black hole, they merge, and you work your way up from a stellar mass black hole to a supermassive black hole with millions or even billions of times the mass of the sun. But that's a lot of black holes finding their way to each other. Well, maybe if you get those first stars forming very quickly with tens of thousands of times the mass of the sun, then maybe you get black holes with tens of thousands of times the mass of the sun, and they merge together, and that you're able to climb that mass ladder more quickly. So figuring out how the first stars formed is still a really big challenge, a big mystery in astronomy, and would be one of the most exciting things that people could discover. John R. Wachowski, would you go to Mars if asked to? I don't know if asked to. How would that work? Like, someone would come up to me and go we need you to go to Mars. Get your ass to Mars. Okay, I guess if I'm forced to go to Mars. Would I travel with a team of astronauts to go and explore Mars? Probably not, I think. I would let other people do that. It's kind of like if someone said, would you be willing to go on a hike to the top of Mount Everest? Like, I hike. I do multi-day hikes. I do a lot of stuff in the outdoors, but that's a level of danger that I am not ready to put myself into. And Mars is the next level. I mean, you're going to commit several years. You're going to have to experience large amounts of radiation. You're going to increase your cancer risks. You're going to be away from your friends, your family for years. You're going to help humanity's exploration of Mars, which would be super cool. And you'd be on Mars. You'd experience low gravity. You would be being on this other world. You'd be living the sci-fi dream. But I think that would get old pretty quick. So your first day, you'd be like, "Whoa, this is amazing. I'm on Mars." And you're talking to the other astronauts like, "I'm on Mars. I know, right? We're on Mars." And then the second day, you're like, "Oh, wow, it's Mars. But there's no water, there's no oceans, there's no trees." And you've got to be there for 18 months. And so near the end of it, you're going crazy. So I don't think I'm cut out for that. But I know the people are. And so I'm why would I want that seat? I would let other people take that seat. Now, I would go to the moon if it was safe. If the moon was people went to the moon all the time to go to the big amusement park on the moon. That's a Futurama reference. I would do that. That sounds great. But I'm not going to be one of the first people to go to the moon. Again, very dangerous. There are people who are willing to put themselves in that kind of danger, not me. So I think someone said I'd go to Mars after Elon Musk's grandma goes. I think that's a good, that's a good description of when to go. Is, when you're taking elderly people on cruises to Mars, it sounds like it's safe at that point. Austin Sapp, do we know of any moons that have moons orbiting them, like moon squared situation? So what you're talking about is known as a moon. That is, that's not the scientific term, but I think that's what we're moving towards as the generally accepted definition of a moon orbiting around a moon. And we don't know of any moons, and it's theoretically possible, but it would require like really careful setup for you to be able to get that, because every planet, every object gravitationally has this thing that's known as the Hill sphere. And this is its region of gravitational dominance. And then at a certain point, other objects can then capture them away from you. So the Earth has its Hill sphere, the moon is trapped in it, the moon is going around the Earth. But if you tried to put something in orbit, say geostationary orbit around the moon, it is outside the moon's Hill sphere. So anything that you put in orbit around the moon will just be captured by the Earth. And so if you tried to give a moon to the moon, then eventually the Earth would try to capture that moon. There's like a few places in the solar system where it would theoretically work. Like if you took Neptune and you moved a moon out to exactly the right distance, and then you put a moon around that moon, then the whole thing could be stable and would last for the age of the solar system. But we haven't found any, and that's probably just because they're not stable. But I mean, when you think about the way the universe works, like gravity, it's all just cycles, right? You've got superclusters with galaxies orbiting around the supercluster, and stars are orbiting around inside the galaxy, and there are planets orbiting around the stars, and there are moons orbiting around the planets, and then there are satellites flown by aliens orbiting around those moons. So, it's fractal, man. All right, those are all the questions that we had this week. Thank everyone for your support, everyone who joined me live for the show. We do this every Monday at 5 p.m. Pacific. So if you want a twice as long episode and have conversations with other space fans as well as me, and we chat about it, there's the regular show, and then there's the overtime. Come join the live show. There'll be a reminder somewhere here on the channel for the next event, but it will be a Monday at 5 p.m. Pacific, unless I'm watching the eclipse. Huh. All right. Anyway, there will be more live shows coming up in the coming weeks. Now, I'm going to talk about another smaller space YouTuber, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, Antonio Lofilara, David Gilton, Dougie Stewart, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Mark Anstis, Paul Rohrbach, Stephen Krasaki, Stephen Fowler Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other patrons. All your support means the universe to us. I have been directing you towards YouTubers who are doing a great job here on the platform, and yet for some weird, bizarre reason have less YouTube subscribers. They're sub 10,000. We have to fix that. So this week, I want you to check out Kyle McCaslin, who is an amateur astronomer, teaches you how to do astrophotography, but also talks about both the gear as well as how to view transits going across the sun, how you can see planets during the day with a telescope if you're very careful and you know where to look. So very cool channel. I really like that kind of practical, hands-on, I've got a telescope, here's what you can do type of material. Great astrophotography as well. So check out Kyle McCaslin's channel. And again, tell me if there are YouTubers that you like, people who are great science communicators, but for some weird reason have less than 10,000 subscribers. Let me know so that we can promote them and get them more subscribers. All right, we'll see you next week.